What's up, you guys? Welcome back to the channel, and today I'm going to show you how to create a physics program that will solve physics problems, kinematics problems for you using Python completely from scratch, and we're going to use the Tkinter graphical user interface package. So in general, there are four main equations in the field of physics called kinematics, which is basically, I'm going to try to pull it up on this website here. But basically, there are four equations that tell you things about displacement, time, initial velocity, final velocity, and acceleration. And these are all assuming you're in an environment where you have a constant acceleration. But the cool thing about kinematics is from three of those variables, any combination of knowing three of these variables, you can solve for the other two. The only thing is there's a lot of manipulation of those primary four functions that has to be done to know how to do it. So I thought it would be a really cool programming project and a really cool cross-disciplinary project to show how to solve physics problems using Python knowledge. And what you'll see as we get through this, and I'm going to show you how to write it line for line, is they're actually pretty simple equations, and we just need to set our program up to make these simple decisions for us. So the app we're going to build visually is going to look just like this. We're going to prompt the user to enter known values, and then they'll have a spot where they can enter displacement, time, initial velocity, final velocity, and acceleration. Then all the user has to do from there is press which variable they're solving for. So if you had a displacement, say you went 123 meters in 2 seconds and you know you started from rest. Well, then if you want to know what the final velocity would be, it tells you 123 meters per second. I guess that makes sense. But then if you want to know the acceleration, it would tell you 61.5 meters per second. And we're going to make the project in such a way it shows you the formula of how it got there. And then you'll be able to quickly clear values. In the off chance you try to solve for something and you don't have enough values entered, it'll even tell you it needs to have at least 3 known values, problem not solved. And then again, if for some reason you were to type in like 9.8 is my acceleration, and then you try to solve for acceleration, it'll even tell you A is equal to A and just output what you entered. So this is a really cool little widget. It's kind of a neat crossover between computer science and physics, and I'm going to show you how to do everything start to finish, including the visual elements in Tkinter. So follow along. Let me know in the comments if you get lost and have any questions at any point. I will probably leave the code for this project in a GitHub that I will link in the comments or in the description of this video. Be sure to subscribe to the channel, leave a like if you enjoyed this or any of the other projects you've seen here, and let me know in the comments below what you'd like to see in future videos. I've really been appreciating all the feedback on recent stuff, and thank you all so much for the support. So let's get into the video. All right, so to get started, I'm going to import 2 modules that I know that we're going to need. So we're going to need the Tkinter module, or some people call it Kinter, some people call it Tkinter. I'll probably say Tkinter, but sorry if that drives you nuts. I'll try not to say it more than I have to. But that's the graphical user interface we're going to use on this video. If you're not new to the channel, you probably know I do a ton of stuff in Pygame because it's fun for like games and easy like widgets. But Tkinter is actually super easy for like data processing and buttons and kind of computer applications. So I think this would be a great one to use for this. And then because we're doing a lot of math, we're going to import the math module. It'll let us use like square root, and there's some other neat stuff you can do with it. I think for this video, we'll probably just need square root. And then what you want to do is just say from Tkinter and then tell it to import everything, and just like that. And now anything in the Tkinter module we can just access through this program. And so just to set up our application, because that's what we'll do first, it's root equals and then just TK with a capital T like that to get a basic window set up. And then just set your title equal to whatever. I'm going to call mine Kinematics Engine because it sounds cool and sciencey, but you can call it whatever you want. And that's what we're going to start with. And then I think what we'll do first is we will draw everything onto the screen. So we'll get our app looking the way it needs to look, and then we will add the functionality to it afterwards. Maybe some people would prefer to do that backwards. Too bad, it's my project. So we're going to do root.main loop just so we don't forget at the bottom. And this is what's going to actually let our application run. So I think if we run this right now, it'll give us a little window. That's how easy it is to get like a window open in Tkinter, just those lines of code. But obviously there's nothing on it. It doesn't look very good. So let's start adding some stuff. And if you're thinking back to kind of the intro to this video, we're going to start with a label. And what's cool is since we have a couple labels, we'll just call this first one label 1. You could call it title label or whatever. But all you have to do to create a label is use a capital first letter, which is kind of the theme with Tkinter, is the first time you reference something from Tkinter, the first letter is going to be capital most of the time. That's really all you need to know. And then say where you want the label to go. In our case, everything we're drawing will be on the root screen, so we'll just say root. And then what text we want the label to have. And so we want this label to say enter the known variables. And since this is going to be above them, I don't really think a colon makes sense, but you could do something like that if you wanted. And then one thing I think is going to look good is if we just say font equal to bold, so that kind of makes it pop. If you want to play around with the style afterwards and make it look cooler, I do have other Tkinter tutorials on the channel. I'll try to remember to leave a card to them or a link to them. You can play around with the style and some colors and things later if you want. But so to get it on the screen, we're going to kind of think of all of our widgets, all of our pieces in a grid system. And so we set label1.grid, and then we just say where we want to be. And this is the first thing that we're putting on the screen. So row and column are both going to be equal to 0. But here's where if you have like a sketch of the final application, you can think ahead a little bit. I know that we're going to have 5 buttons for displacement, time, acceleration, initial velocity, final velocity, and clearing out the values. And so I want this label to span all of the columns. So this variable column span, I'm going to set equal to 6. You could come back and add that later. You definitely don't have to be all the way planned out when you start creating it. Just know this column span variable is setting how many different widgets can be underneath it, and this one label will span across all of them. So we're going to say column span is equal to 6. And then 2 things I like to set for almost every widget are just pad X and pad Y, because I think apps don't look that great when they're stuffed up and like your buttons are touching one another. But if you like it, you don't need that step. You don't have to follow along with all of the style things that I do. I just think padding looks good. And then this sticky variable is actually very interesting. This is saying if I resize the window, do you want the widget to resize with you? And so north, east, south, and west basically means top, bottom, left, and right. Not in that order, don't quote me. But essentially, when you resize your window, if you do have this sticky on there, so let's go ahead and run that. Enter the known variables. Now, if I start stretching this thing out, well, actually, it's not going to do anything because we don't have any other widgets on there. But it's saying that this field, because the text isn't resizing, but this field, this widget technically is spanning the entire width. So we're going to be making pretty much every widget we make sticky just because I like it resizing. If you're building an application that you don't want to be able to have resizable, then you don't need these sticky pieces, okay? So now that we've put that label on the screen, we need to make labels for all the variables as well as data entry fields. So I'm going to kind of go quickly through here since we're doing sort of what we just did every time. We're going to start by making a displacement label, and I will just call it D label. And that's going to be label and then root, and then the text for this one is going to be D displacement, and then let's tell them units, because the other thing is if you were using this physics engine, this kind of application, and you didn't know what units, the formulas are set up to use standard units, so like SI units. So they would have to convert if they had something in like feet or miles before using these functions. Okay, so D label, and then we want to do it's going to be everything the same 2 steps. We define the label, and then we define where on the grid we want it to be. Most of the things are going to overlap with what we just put in, so I'm going to go pretty quick. But again, if you have any questions, just ask them in the comments. I'll do my best to get to everybody. So then on the grid, now we're just moving down to the next row. We want it to be in column 0, but we don't want this one to span all the way across, because we want there to be an entry box, which we'll just call D, and we want capital E entry to be on the root. And then all we're going to do is we're going to make it a little bit wider than their default border by saying border width equal to 5, and I think that looks good. And then we'll do d.grid, and I will run it after I get this grid so that we can see the first one, make sure we kind of like the style, and then keep going. So this is going to be in that same row as the label, only now it's going to start at column 1, and it's going to span the rest of the columns. So let's go ahead and run this just to make sure we like how it looks. So now you can see enter the known variables, and we have D displacement in meters. And that looks pretty good. So we're going to just kind of copy those 4 lines, and we're going to go pretty quick here, but we're going to set the same thing up for A. So D, let's do T second, just because we have to do all 5 eventually. Order doesn't matter too much. And then T is T, time, and the units for time are seconds. Very good, class. And we're going to put that now. These guys are going on row 2. And then the column width and column span can stay the same. So now let's copy the D's and the T's. D's and T's. And we will do VI and VF next. So we'll save A for last, the acceleration. So VI and VF are initial velocity and final velocity. If it would make more sense to you to use a different way of referring to them, you go ahead. VI and VF works pretty good for me. So we're going to say VI initial velocity, and just to keep it not too long, I'm just going to say M per S, and then VF is final velocity, and then again that is meters per second. And so let's do one more of these. Let's grab T because it's just a single letter, and we're gonna do A now. Oh, actually I think I didn't update the row, so you gotta be careful about that when you're copying and pasting. Yeah, these guys need to be row 3, and then these guys need to be row 4, and so these last ones will be row 5, and we'll do A now. A now, you're an all-star. Okay. Stupid joke. And A is acceleration. Acceleration. And that is meters per second squared. And the actual Python formula for doing raised to a power is this 2 multiplications, 2 stars. But I think the thing most people would be more familiar with is the caret. And since this is just for display purposes, we're going to put the little caret in there. But you'll see when we get to the math, the 2 stars is how you actually do the math. Okay, so that should give us everything for the entries. Great. And now let's put the buttons on the screen, because that's going to be selecting what the person wants to solve for. So let's grab label 1, because we want to do a label 2 telling the person select what you want to solve for. So label 2, and then this is going to be row 6 because we're moving right on down the screen. And we will say select what to solve for. We'll put that in bold again, same padding, that should look fine. And now let's put some buttons below. And the buttons are kind of cool. They're all going to go on row 7 because we'll just stack them up right below the label. So let's start with a clear button actually. And we will just say clear button equal to capital B button. So this is a new type of widget. We'll put it on root again. Let's make the text just equal to clear values. And then all buttons need to do something called command, otherwise they're not going to do anything. And so we're going to create some functions now that we'll fill in later for each button. And then the last thing we'll do is we'll say font equal to bold for all these buttons. But so the clear button is going to run a function called clear values. And what we can do initially while we set this up is just make these placeholder functions and put one line in, put pass, and we'll come back and we'll actually fill them in, reminding us that we need to populate these various commands. So clear button, and then the second piece, as always, is define the grid. And I'll say really quickly, you could do this all in one run on line. You could do define the button and then dot grid and then give it a row equals, a column equals, and do this whole dot grid stuff after this definition. It's way cleaner to put it on a second button, and it's not like your program is going to be too many lines of code. So just put it on a second button, unless for some reason you are just jonesing to have like a sweet multi like 160 character run online. So don't do that to me. Okay, so the clear button we're going to put over all the way to the left. So it's going to be column 0, row 7, next line down, and we will copy these two for clear button. And we are going to make well, let's do it in the same order. D, T. So let me not lose track of this. So the D button, the T button. I think we did VI, VF, and then A. So D button, T button. Then this is going to be VI button, and we need two more, so we will call those VF button and A button. A button, real descriptive, Pete. Okay, and now let's just make sure we update everything. So the columns are going to increment, so column 0, column 1, column 2, column 3, column 4, and column 5. So now, starting from the left, everything always starts at 0 in programming. It really rarely starts at 1. You should know that by now. So 0, 1, 2, 3, 4, 5, these will all be on the same row, and I think this will look pretty good. So let's just put, instead of clear values, that says D, that says T, that will say VI, and I think it's okay that we just show the abbreviations, because on the labels we're showing the full name of everything, and we'll make them all bold so that it pops. And then one more thing, let's just plan ahead and let's put a little field down below. It'll just be a label, but it's going to be where we show the results, so I'm going to call it results. And you do something neat when you have a text that's going to be changing constantly inside of a label. You use text variable, and let's just say results underscore string. So this is going to be a string that we need to keep track of. But when we solve for things, all we have to do is populate the results string variable, and then the screen is going to automatically update. And so again, we'll say font equals bold for that. And then let's put this on the grid, results.grid, and we will put this, it'll be kind of similar to the label, so I'm going to steal the grid math for the label because it's going to span the whole screen, and we want on the next row down. So 8, and then column span is going to be 6, that's okay. And now we have to do a few things, because actually I left all these commands as clear values, but this is going to be calc D, so do some math to find the displacement. This will be calc T. Then we are going to have calc VF. It looks like I'm off by 1 actually. This is calc D. Oh boy. So calc D, calc T. Yeah, make sure you get the right variables for each of your buttons, or your math isn't going to make a lot of sense. Okay, so you can see we're getting these red squiggly lines. We have to go up and we have to make all these functions. So let's define those functions real quick. We have calc D, and for now that's just going to pass. And then define calc T, and that's just going to pass. And then we're doing the same thing. And it may seem a little repetitive here in the beginning, but I promise you it's because we're creating all this framework. So once we get working on the actual math to solve the physics problems, we can just rock and roll, and that's going to go really quickly. So define A is going to be the last one, calc A. And then one more thing we have to do, because obviously that's not the only red squiggly lines we had. We also were getting red squiggly line under results string because we haven't defined that yet. So go back up to the very top. Technically anywhere before you call for it is going to be an okay spot, but right underneath your import statements, let's just say results string results string is equal to, and this is a special type of variable that we're going to call string var. It's a you can see if you have an IDE like PyCharm or something, it's a special Tkinter type of variable that lets you update, and make sure you put parentheses after it. And then because we have a variable, we need to set it initially, so we'll just dot set, and we'll make it all caps, just say results in the beginning, so we know what will eventually go there even though nothing goes there yet. And then actually let's take these two root statements and just put them up here with our initial stuff. So we kind of have like initialization code, and then we have all our Tkinter, so I'll say Tkinter visual elements, and then all these functions are going to be like functional code. Okay, and so I think if we run this real quick, what we'll see is we have a really cool looking HMI, but what you'll also see, I say HMI, human machine interface, it's the same thing as GUI, GUI, graphical user interface. It has all kinds of names depending on what industry you work in. But so the thing is, I can enter stuff in these fields. They could be numbers, they could be letters, it doesn't matter, or they could be spaces. I can click all these buttons. It looks great. Like, we just designed the app really quickly. It looks great. But one thing visually before we move into the functionality, none of the stuff is readjusting, even though I told you that's what sticky does, because we haven't assigned any weight to the columns. So this is kind of a weird bit of like Tkinter knowledge. No worries if you didn't know it already, but you want to go through and give grid weight to each column and each row if you want them to resize when you resize your window. And so you just say grid column configure, and then you need to give them weight. So we're going to do it in a for loop, so I don't have to type grid.column configure root 0, 1, 2, 3, 4, 5. So we're just going to do it in a for loop, but you need these statements saying that the weight, and I always just do 1. I believe the weight can be anything between 0.01 and 1, like it's a percentage of 1. But just doing this, and now what you'll see, I hope, fingers crossed, yeah, when I make it wider, everything resizes with me. And if you want the same thing for the Y direction, then you do the same thing. It's just grid.row configure, and we'll see if we actually like the way this looks, and then we'll say root I weight equals 1. And now we have more rows than we have columns. We have 8 rows, so we would have to catch all of those, we would have to do for I in range 9. And to use this, we'll just say while I less than, no, we'll say if I less than 6, because the columns stop at 5. So this is just a little for loop so that we can set all of the weight for our rows and columns so that it's totally resizable. Now let's check that out. So now if I make it wider or if I make it taller, everything readjusts. This is probably what you'll want to go with. Sometimes I don't love resizing the Y dimension stuff because the defaults are usually pretty good, but let's leave it like this for the sake of the project. Okay, now let's just start with one of these functions. So let's start with calculating A. Okay, I know we put that button last, but calculating acceleration is a pretty cool one. So let's just start there. And what we want to do in all of them, but we'll do A first because the code is going to look fairly similar across all of them, is we want the results string to be available inside of that function. And passing parameters in and getting parameters out is kind of a headache with Tkinter. So I'm just going to call a global so that once we know what A is and we've solved for it, we can just update the results string. And then I want to get all of the known values. So remember, this is why we entered all the values in the beginning. And we're going to get the known values in a standalone function that's going to work no matter what we're solving for. So I'm going to say known equal to get known values. And let's come up here and let's create the get known values function. So get known values, and we are returning known values, just like that. So remember, when you call a function, if you're trying to get information out of it, just say information equals to function name, and then inside of that function, make sure you return whatever the information is. And now known is going to be this useful thing that we're going to set up. It's going to be a dictionary, which is key value pairs. So we're going to check what essentially what values were entered. Was it initial velocity? Was it time? Was it displacement? Whatever. And we're going to enter two things in for each entry. We're going to enter basically the name of the variable and the value of the variable. That's the purpose of a dictionary. And to do that, we're going to use a Tkinter function that's just .get. So when you have a Tkinter label or a data entry, and you want to know the information inside the data entry, you just use this .get function. And we basically want to check it was something entered. And so if it's not equal to a blank, then we will say D1, so just this intermediate variable we're going to use, and just do a float conversion of d.get. So basically whatever number was entered in there, convert it to a float, because by default it's going to read it as a string. And then we're going to get that, and then we're going to do this known.update. And actually, when you do an update, make sure you have the curly brackets to let it know it's taking a new dictionary entry. And we're going to say, okay, we have displacement, and then do a colon, and then do the value of it. And so this exact statement that we have right here, we're just going to copy that for all the variables. So if t, if vi, if vf, and if a. And so let's say if t.get. So again, if something was entered for any variable, then we are going to store that value in this library of values. So this will work if you only entered one. This will work if you didn't enter anything. This will work if you entered 5 things for some reason. I don't know why you'd want to be solving for any of these if you entered 5, but it would still work. So this dictionary is going to be scalable based on how much information we have known. And so this last one is if a.get, a1 is equal to float of a.get, a1. Let's just check real quick. A, VF, 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 VI, 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 T, 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 D, 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 D. Okay, so this is just going to go through all of our entries and return the known values. And the reason I want to do that like this is because these first two are going to be in all of the functions. And now we're going to start saying what to do based on those known values. And so the first one's the easiest one. If A is in the known dictionary, and that's all we have to do, because when you say if something, a string, is in your dictionary, it's going to check and see if that dictionary has that as a key. So we're checking if acceleration was in the dictionary and you clicked that you wanted to solve for A. All we're going to do, and now I'm going to use A2 just to keep track of what variable is in what location. You can mess around with naming if you want. I'm going to say A2. It's just going to be equal to the known dictionary at the key of A. So the value in your dictionary that correlates to the entry for A, that's what A is equal to. And what I want to do in the results field is I want to update. So basically at the end of this, before we return, I want to set the results string. So no matter what, I want there to be this results string dot set. And it's going to be a formatted string, meaning we're going to have some variables and we're going to have some text. So to do that, you just do F, and then you can do either double parentheses or double quotes or single quotes to define a string. I'm going to do single quotes. And I'm going to do this in 2 pieces. I'm going to show my work, because no physics teacher is letting you off the hook without showing your work, even if your work was writing a program. And then I want to display the value. And so I'm going to say acceleration. And because we're doing complicated math here, we want to round it so that we don't show a million decimal points, because Python will give you like 10 decimal points as a default. So let's just round it to only show 2, and then always show your units. Otherwise your teacher is going to make some terrible joke about acceleration is 5 what? Elephants? And then you want to flip them off, but you're in school so you don't. Maybe that's just me. Anyways, what we're doing is we need to show our work, and then we want to actually show the value of the acceleration. And I put a new line in there, so we'll kind of separate the work out. Work is going to be important when we actually do functions, but for this one, it's kind of silly because like we don't need to show any work. You told us A. So for A, for work, if A was actually in the known library, we're just going to say A is equal to A. And I like these 3 dots because it seems really logical. Maybe that's just me being sassy. But we're also going to use this formula tracker basically to tell us what math to do. And so I'm going to say formula is equal to 5. You'll see why in a second. But basically, we're checking a few one-off situations here in the beginning. So then we're going to check if the length of our dictionary, so the total number of variables that we know, is less than 3. That means that you did not give us enough information to solve. So what we're going to do is we're going to set formula equal to 0, and then we're going to set our work equal to an explanation of why we can't solve it. So we're going to say need at least 3 known values to solve problem not solved. Okay, and so we're going to tell them that, and then for A2, because no matter what, your error is going to throw a value, or is going to your program is going to throw an error if you don't give it a value at all times, unless you make this result string.set conditional on what like the value of formula is or something like that. To keep mine generic, I'm going to do it this way. And now we need to set up some code to check what variables we do know and what formula we should use. And so remember, I said at the beginning, if you have any combination of 3 variables, you can solve for both of the other 2, which means, sorry about that, which means we need to check what 3 variables we have. If we have 4 variables, we don't really care because there's multiple ways to solve it. We have too much information. But to do that, what we're going to do is say elif, and these can all be elifs because we're kind of doing it in order. If A is in known, done. We don't need to solve anything else. You told us acceleration and then said you wanted to solve for acceleration. But then if the length of the library is less than 3, then we can't possibly solve it. Then we're saying, okay, you didn't tell us acceleration and you gave us at least 3 values. Now let's get solving. So to do that, let's start by checking if vi is in our known list. So that means you gave us initial velocity. And then we'll say if t is in known list, so you've given us initial velocity and time. We'll say then if vf is in known. And so now we're saying, okay, we have initial velocity, time, final velocity. If we have those conditions, let's say formula is equal to 1, and then we'll say elif d is in known. Then we'll say formula is equal to 2. And basically, it doesn't really matter the order you do these in. You don't have to check in the same order as me. Just make sure you check for all possible combinations of 3 variables other than acceleration. So here we see vi, t, and vf, vi, t, and d. Then if we go back a layer, because that's all there is at that layer, we say, okay, we have vi, but we don't have t. So now we check if we have vf in known, and make sure you get this in known every time, and d in known. So now the reason we did those at the same time is because we checked if we have vi, t, and vf, or vi, t, and d. And the next combination would be vi, vf, and d. And then the only remaining condition, so other than assuming they give us this, let's just do it as another elif. We'll say elif vf in known and d in known. in known and t. I see, I get tripped up. So the one thing we hadn't checked for up to this point, and I forgot to say formula will equal 3 in this situation. The only one we hadn't checked for up till now was if we had VF, D, and T. And if that's the case, then we will say formula equal to 4. And if we have some other situation, let's just print what is happening. Because it's not supposed to be possible to have any other situation, but sometimes if you leave yourself clues like that, if you run into something weird later on, then you can usually debug a little faster if you throw an else statement in there. You don't need that. I just thought that was funny. Okay, let's actually start using the formulas now. So what we're going to do is we're going to say if formula is equal to 1, which means we have T, VI, and VF. Then we have to actually store those in variables. Otherwise, this is going to be really messy. So we'll say T2 is equal to the known library value at the key T. And we're going to use this exact format a lot in this program. So T, and then we are going to do the same thing for VI and VF. And we are just going to say VI and VF just like that. And now the thing is, I'm not going to spend a million years on each kinematics formula and explaining where they came from. So basically, if you look up here, I'll throw these in. So if you do decide to grab the code, kinematics equations, using editing magic, they're all going to be there now. And what you'll see is these are the 4 functions non-manipulated in any way, not multiplied or pushed around or subtracted to isolate variables. But these 4 variables, these 4 functions give you a way to solve for any 2 variables with the other 3. If you know the other 3, you're going to have to trust me on that. Again, I'll show my work, and I explained how I'll be showing my work, but I'm going to go pretty quick through the formulas. So if you have any questions, again, let me know in the comments. I'll get back to you when I can. Get known. Oh, and I called this get known values. So let's just be consistent there. Okay. And now, when we have T, VI, and VF, the formula for A is going to be acceleration is just equal to VF minus VI divided by T. So that's the formula. You're going to have to trust me on it, or you can go extrapolate variables on your own if you want. And then to show my work, so this is what I want to go on the screen. I want it to look pretty clear. So I'll just say A. You don't need those 2's in your work. This is just a string showing what formula we use to get there. So I'm going to say VF minus VI divided by T is the whole function. So there we go. And now when we run this, if we give it T, VI, and VF, it's going to give us acceleration. So nothing else is going to work yet, but we might as well try that. So let's say we have a final velocity of 10 meters per second, an initial velocity of 0 meters per second, and we get there in 3 seconds. What's our acceleration going to be? I'm good enough at math to say it's going to be 3.33, but let's hit A. So there you go. It shows us the formula that we used, A equals VF minus VI divided by T, and it shows us the final answer, which is acceleration is 3.33 meters per second squared. So that's pretty cool. We are one step closer to having this thing as a fully functioning project. So if you were here for the concept and you don't want to watch me type in the formula for all 4 iterations for all 5 variables, maybe now's a good time to grab the finished code from the GitHub. Otherwise, if you like following along and you're enjoying the concept, let's just keep rocking and rolling. So then we'll say elif formula equals 2. Then we have the same variables, except now instead of in final velocity, we have D. So we are going to grab those same 3 things. We had T, VI, and VF before, and now in 2 we have T, VI, and D. So honestly, a big part of this project is just keeping your head straight on what 3 you said you had up here. So we said VI, T, and VF. then VIT and D, and then VIT and or VI VF and D, and then VFD and T. So keeping those variables straight and making sure you get them in the right order is going to be important to processing data the right way. So just be careful about that. That's like #1 programming tip, is just slow down, take your time, think about what you're doing when you're doing it. Okay, and now the acceleration formula for this one, we have to push some values around a little bit. So again, I'm not going to show you the full like, oh, you have to turn this formula inside out and backwards. But basically, one of the formulas we have, the variables in it are, let me scroll back up to the kinematics formula. We have T, initial velocity, D, and A. So if you look at the formulas, what formula uses T, initial velocity, D, and A? It's this top one, but it's initially set in terms of D. So I'm not here to give a math lesson, but if you wanted to separate it out to where A was just on one side, then you would start by subtracting VI times T from both sides, and then you would have 1/2 times A times T squared, and then you would want to multiply both sides by 2 to get rid of that 1/2. So then this would become 2 times D minus VI times T. You would get rid of that. And then you would want to divide both sides by T squared to get rid of the T squared. And that would give you this formula A. So it's important to realize this is the same formula as we have right here. And for the sake of programming, we have to be smart enough on our end to realize that and turn it around so that we can use it. Your physics teacher probably wants to know that you're smart enough to do that on your own, but I'm trying to help you do your homework a little quicker, and maybe you like programming more than physics. Okay, so that's what we did here, is we turned that formula around and we solved for acceleration. And for our work, we're going to basically show the formula we turned around and just say A is equal to 2 times, and then the result of D minus VI times T, and then the whole thing gets divided by T squared. So that's the work, and that's the function. And now the next one uses VF, VI, and D. Again, keeping that square is going to be the hardest thing. And then once we have one of these fully set up as well, it goes a lot faster for the next 4 variables because we have this kind of framework to build around. So now we're saying, okay, D2 is the known value of D, VF is known, and VI is known. And so for this one, acceleration is equal to, and this one's nice, it's just a straight formula that we already had, VF squared minus VI squared. And don't let these 2's confuse you. The VF2 and the VI2 are the variable name. And then 2 stars, like I said a little earlier, is the Python method for raising something to a power. And so that's saying VF squared. That's all this is saying. Minus VI squared and divided by 2 times D is how we get acceleration. And so to understand that one, we go back to our root functions here. And this one's really easy. It's VF squared equals ordinarily VI squared plus 2AD. Well, all we do is VF squared minus VI squared divided by 2D is going to equal A. So you're all scientists. You know what we're doing at this point. I keep telling myself I'm going to stop explaining it, but there you go. Okay, so the last one for acceleration is formula equals 4, and keep in mind what we said formula 4 was, VF, D, and T. Okay, and this one is kind of tricky. Not really, as you'll see, but it's a little different because there's no kinematics formula to solve directly for A without first solving for initial velocity. So if you look at the kinematics formula while I'm typing these out, even though before this I've been copying them every time. So we have D, we have VF, and we have T, and known value of T. Okay, so we have D, we have VF, and we have T. Well, let's look at our kinematics equations, because remember, we're trying to solve for A. There's no function that uses A, VF, D, and T. Okay, there's a function that uses 3 of those, and that would solve for vi. But like here, any function that has a in it also has initial velocity in it. So I didn't lie to you. We can solve for a as long as we have 3 values. But first we have to solve for vi. So what we need to do, and we haven't had to do this before, is we actually have to solve for the other unknown variable to solve for our unknown variable. So in this case, we're going to use that function that has dt, vi, and vf, and we're going to just need to solve for vi first. So to do that, we're going to say d divided by t times 2 minus vf is equal to vi. So this, I'm totally bluffing, but this is probably the last time I'll show you where we get this from. Let's go back to the equations. This one is d equals vf plus vi divided by 2 times t. We need to solve for vi. So d divided by t, I'll go ahead and copy this one. D divided by t gets rid of that, and then 2 times d gets rid of that, and then all we have to do is subtract vf from both sides, and then it's vi equals 2 times d divided by t minus vf. Okay? So there we go. That's kind of the manipulation we have to do to write this programming, but it's pretty slick after that. And once you solve that, solving for a is really easy because we have all the other values. So we actually have 3 functions we could use to solve for a. So you don't have to use this one if you don't want to. I usually try to lean for the one that looks the simplest and it's the simplest to type. But now the thing that I like to do for this, maybe you think it's overkill. I think for the work, it's really useful at this point to then show our work and the steps that got us there. So to start, we're going to say, okay, vi equals 2d divided by t minus vf, and then let's do a new line, and then let's say vi is equal to, and then actually show vi2, and then meters per second, because your teacher will make a joke about units. And then, so now we've explained how we got vi, and now we just show the formula that we used to get a. So we say a is equal to vf minus vi divided by t. And I'll put these in parentheses just because looks better. Okay, but now we give acceleration. We try to solve for acceleration with any combination of 3 known values, and we're going to get an answer back. So let's go ahead and play around with this real quick. Let's just say we go 100 meters in 12 seconds, and we started from rest. What was our acceleration? And I get an error. Unsupported operand for type POW. Yep. So let's see. That was one of the ones that I squared here. So this is one of the reasons our naming conventions can get kind of goofy. This needs to be T2, not T, just like this. So remember I said don't let the powers trip you up, and then I immediately let the power get to me. So fight the power. But make sure your variables that you're actually doing math with all have that 2 afterwards, or you could use a less confusing naming convention like math. Or you could do like t underscore math or something like that. Okay, let's say you're going 2 meters per second. You go 12 meters in 3 seconds. What's your acceleration? 1.33 meters per second squared. Okay, not bad. I don't even know if that's right. Final velocity is 2. How fast are you going? You're actually accelerating negatively. Cool. Okay. What we are going to do to check this at the very end once everything is made is there's a site that gives you sample kinematics problems to check this against. If you have a physics textbook, you could check it against that. But now that we've done calculate A, I'm going to do one of the easy functions real quick, which is clear the values, just because that's going to take no time. So to clear out an entry after you've done, so maybe you want to solve for something else, you just solve for acceleration, you want to clear everything out, you just use this, so it's the name of your entry, dot delete, and then from starting point to end point, and we want the whole thing cleared out. So it's d.delete 0 to the end. That'll make it empty, and we're going to do that 5 times. So d, t, vi, vf, and va, just .delete vf, and that's it. So now I'm going to run this, punch in some values, 12, 3, 4, 3, and we didn't solve for acceleration yet. Okay, I didn't see the values, but hit clear values, bam, and everything's gone. So clear values is done. We've now done all of the calculations for A. Basically, everything inside of this function, we're going to copy, and we just need to modify now to be specific to all the other variables. So I'm going to try to go pretty quick through the next ones because this is really the tedious part of the programming. And if you understand the physics concepts going on and you understand what we just did for acceleration, it might be a really fun point for you to move on and kind of try the next one on your own. So I'm going to do final velocity, and if you want to keep following along, let's do it. So now instead of A being known, we're checking if VF is known, because if VF is known, we can skip over everything else. Again, if we don't have 3 values, then we can't solve and we don't need to move on. And we want at the end, instead of showing our work for acceleration, we're showing our work for final velocity. Goodness, there we go. And that's not in meters per second squared, it's just meters per second. So now the fun part, I guess it's the fun part, I like doing it, is actually checking for the variables. So let's start with VI, and then let's check for A, and then let's check for T. That'll be what we call formula 1. Then we'll say else if it's VI, A, and D, that'll be 2. And then we'll say else if it's VI, T, and D, that'll be 3. And then we'll say else if it's A, D, and T, that'll be 4. Else leave what is happening, that'll work. And so basically you just need to make sure you have all the combinations. So now we have T, VI, and A as our knowns. Just make sure you're updating these and being consistent. And VF is going to be equal to, so VF2 is equal to VI plus A times T. And that's probably the easiest one of the whole night. So VI equals A times T. And all we have to do to show our work is say VF equals VI plus A times T. There we go. Now 2 is still pretty simple. It's going to be dA and VI. So dA and VI. And the function for that one is, now we just have to use the square root. So here's why I imported the math function, because I knew there were square roots coming. Python does not have a built-in sqrt functionality. So what you do is you type math.sqrt and then open a parentheses, and it's going to square root everything inside that parentheses. Okay, and so math.square root, and then it's going to be vi2 squared plus 2 times A times D. Again, just coming from those same kinematics, not raised to the 22nd power, just to the second. Careful on all your units. And for our work, we're just going to kind of explain what we did there. I don't think we need to type out math.square root, so we will just say VF is equal to square root of VI squared plus 2 times A times D. There we go. And it's up to you if you want these multiplication symbols in there or not, but I am going to opt for yes. Okay, so formula 3 is dt and vi are our knowns. So dt and vi are our knowns. And then we say vf2 is equal to, and just twisting our formulas around a little bit, d2 minus t2 times 2, and then minus vi. So this looks very similar to one we did for acceleration because we had to solve for vi first. So it was vf minus this, or it was actually this minus vf equaled vi. But it is the same function, just twisted around a little different. And again, it is 2dt minus vi. That's the whole thing. That's our work. Good job, everybody. And then for 4, we have D, A, and T. D, A, and T. Sometimes I wonder why I promise to show you guys things line by line. It just makes my life harder. Okay, so again, for D, A, and T, you'll notice we don't have any function that has D, A, T, and VF in it because of the same reason that we just didn't have D, A, VF, and T in it when we were solving for acceleration. So again, we're going to use those 3, D, A, and T, to solve for VI by saying VI is equal to D2 minus, and then it's 1/2, which we'll write as 0.5, times A times T squared, and we'll close that up, and then we'll close that up and divide the whole thing by time, and that's how we solve for initial velocity. And then final velocity is just equal to initial velocity plus A2 times T2. So even like there, I typed just T instead of T2 again. Gotta keep an eye on those 2's. It gets a little confusing, but I still think we're doing this in a pretty logical way. So here, let's show our work, and this time it's a little bit harder to show, but D minus 1/2 times A times T squared, and then the whole thing divided by T. Oop, back. There we go. The whole thing divided by T so that we can solve for VI. VI is then still going to be equal to VI. And then that means that A, this time instead of A, we want to say VF equals VI plus A times T. There we go. Okay, and that's everything we need for VF. Let's carry on because we're doing pretty good here. And this is already about an hour-long video, so I don't want to chew up too much of your time. Let's adjust the VFs for VIs. So as always, we want to start by checking if VI is already in our knowns library, or if we don't have at least 3 known values. And then let's just, so we don't forget, at the end we will say initial velocity instead of final, and we will have that be VI instead of VF. And now let's go through and make sure that we are checking for every combination of variables. So let's start with elif A, D, and T, and then we'll say, okay, not A, D, and T, what about A, D, and VF? And then we will say, okay, A, T, and VF. And then the last possible combination is going to be VF, T, and D. Quick water break. Alrighty. Now let's go to Formula 1. So that's T, A, and D, we said. You know what? Let me check real quick. I'm not completely sure. Did I update the inside values of all of these? T, VIA, A, VID, D, VIT, D, AT. Yeah, that one looks good. Okay, T, VIVF, T, VID, D, VIVF, D, VFT. Okay, I was good. I just wanted to make sure I didn't miss something in these tutorials. So, all right, Formula 1 is going to be T, D, and A. And then VI is just going to be equal to, and this one, it's a formula we've already used because we just used it to solve for VI so that we could solve for VF, but it's going to be A2 times T2 squared, and then the whole thing divided by T2. So that should be pretty familiar. I'm actually going to steal the work, I think, because we already typed that function out right here. VI is this, yeah, this whole bad boy. So I'm going to copy that sucker, and we are going to come use it for our work. Where the heck am I? Here I am. Our work here. There we go. That maybe was slightly faster than just typing it. Okay, next up is going to be D, A, and VF. So let's update that to be VF. Shoot, I'm updating 3. We're on 2. D, A, and VF. There we go. Yeah, I know you guys are tired. I'm tired too. Suck it up. Okay, VI, and then math.square root this time it's VF squared, and instead of plus, it is minus. But that's pretty cool how close it still is because we are smart. And then that's VF, and that's minus. But that's 1 and 2 done, A, VF, and D. Now 3 is A, T, and VF. 3, A, T, and VF. And the best part of VI is it does exist for, it's in all of the formulas, so we're not going to have to do any two-step stuff like we have for other ones. Okay, so to actually solve for VI for formula 3, it is just going to be VF, so final velocity minus acceleration times time. That should logically make sense to my scientists out there. And then VI for our work that we're showing to explain the formula, we'll just say VI equals VF minus A times T. And now we are on to 4. 4 is D, T, and VF. And then VI is equal to D. I'm going to get rid of this two-step. We don't need it. VI, when we know D, VF, and T, is equal to D2 divided by T2 times 2 minus VF. These should be looking a little familiar because there's only so many ways to turn around the same 4 functions to solve for these 4 variables, but it is important to understand how they all work. Okay, so let's see, I put too many quotes there. To show our work for this one, we are just going to say VI is equal to 2 times D divided by T and minus VF. That's it. Okay, and now we're done with final velocity. And if you don't believe me, we're going to get to the test at the end, but we are going to keep rocking and rolling because I know how long this is taking, and I appreciate all of your patience and your continued interest. Give yourselves a pat on the back for having a long attention span in the TikTok era where everything's 6 seconds and you just click off of videos as soon as you click onto them. You're here an hour in. Go you. Alrighty, so let's do T next. Alright, so if T is in known, then we're going to set T equal to the known value, give them a sassy little ... And if it's less than 3, we can't solve. And then at the end, we will still show our work. We will still round time. But now, we instead of acceleration, we say time. And units are seconds. So we'll type SEC just to be ballers. Okay, so as always, you guys guessed it, we are going to make sure we have all of the variable combinations. So for T, let's just start with VI because it's already there. And then we'll do check VI, A, and D, VI, A, and VF. And next would be VI, VF, and D. Wow, this is really close already. And then VF, D, and A for 4. Alrighty? And let's dive right into these because we are actually going to have a very unique one here first. So in the scenario that you have A, VI, and D as your 3 knowns initially, so A, VI, and D, you have to do the quadratic equation. And I maybe just scared some people because I know no one wants to do the quadratic equation. I don't want to do the quadratic equation. I don't like math. But if you look at this, the function that has A, VI, and D, and you're trying to solve for T is this one. It's the one that is D equals VI times T plus 1/2 A times T squared. The quadratic equation, if you have forgotten it, is, hang on, I'm going to use editing magic. The quadratic equation is x, so what you're trying to solve for is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a in a situation where you have a variable in the form of ax squared plus bx plus c is equal to 0. Okay, and if we're going to do that, then what that means is in the terms of this kinematics function, that means that a is equal to 1/2 a. which means it's the 1/2 a. It's the constant attached to t squared. And then b is equal to vi. And then c is equal to negative displacement, because you have to subtract this over here to get it in this form. So to do that, we are going to do the quadratic equation. I think that's the more intelligent way to do it. It's better practice for programming. I guess technically it's valid to say that if you're trying to find t and you have a, d, and vi, you could solve for vf. So let's see. You could solve this function and then solve it any other way. But I want to show you guys how to use the quadratic equation, because there is a formula that will let you solve directly for t without solving another formula. So to do that, we're going to say t plus is equal to, and now we're just going to type in the quadratic equation. So we said b, so it's negative b, so it's minus vi plus, and now we need to put a whole bunch of stuff in a square root bracket. And what'll be in a square root bracket is b squared, so vi squared. And then we have to do a plus and a minus. So for this one, we're going to do, that's why this is a plus. Remember, it's b plus or minus the square root. This is going to be t plus, and then we will do the same function right below. That's going to be t minus. And the reason we're doing that is this function is always going to give us two values. And time can never be negative, right? You're never going to be able to solve for a negative time. So you want to check if the solution is positive or negative, and whichever one is positive, that's your answer. Okay, so it's b squared minus 4 times a, which this gets a little confusing because it's a over 2 is a, and then times c, which is negative d. Okay, so there's a lot of goofy letters here, but if you followed along while I was explaining the first bit, hopefully this part still makes sense to you. And then that whole thing that we've typed in so far is just divided by 2a, and again, that's 2 times a2 divided by 2. So I'm going to sweeten things up a little bit and just say divided by a, because 2 times a divided by 2 is the same as just a2. And then I'm also going to simplify this bad boy a little bit, because 4 times a over 2 is the same thing as 2 times a. All right, so we have 2 times a. We can get rid of some of these redundant parentheses, although actually that's negative, so those aren't redundant. And we can copy this entire formula and just change the plus to the minus. And now what we're going to say is if t plus is greater than or equal to 0, then t is equal to t plus. And now on the off chance else, t is equal to t minus. So good job. You just automated the quadratic equation inside of automating a kinematics function. So you guys are so smart. Okay. Now the work for that one is kind of a pain in the butt, because I do think that the right thing to do is explain how we got here by saying 1/2 times a times t t squared, forgot where the caret was, plus vi times t minus d is equal to 0, and then backslash n, and we are going to say quadratic equation x equals, and then we will just show them that we know what the equation is. It's negative b plus or minus the square root of b squared minus 4ac divided by 2a. And that should really get your math and physics teachers excited to be here. They're having a good day now. Backslash n, and I'm just going to hit enter because I want to type on the next one. So the final stage is actually t is equal to negative vi plus or minus the square root of, and then vi squared. It doesn't matter if you put a negative there or not, because honestly negatives are always positive once you square them. You should know that. and then divided by a. So this is kind of us showing that final step, how we actually got t, and it's going to be the positive of. So it's the positive one of these two, because the nature of this being a plus and a minus is one is probably always going to be positive, one's always going to be negative, and the reason I'm saying if t plus is positive, on the off chance they're both positive, which there are probably a few weird scenarios where it could be. I haven't taken math in a while. T plus is going to be the more positive one, right? Because this is going to give you a more positive number. You can't do a square root of a negative without it being imaginary. All right, so that's our work. That was a pain in the butt, but that is the only time we have to do the quadratic equation. And honestly, if you weren't able to follow along with that, just solve for VF first, and then you can solve for T directly. Okay, so speaking of VF, formula 2 for solving for time, we are solving for time, right? Yep. Is going to be assuming we have A, VI, and VF. So update our knowns. VI, VF, and now easy, direct, no quadratic equation. T is just going to be equal to VF2 minus VI2, and that whole thing gets divided by A2. Just like that, okay? And our work for this one is really easy. We just get to say T is equal to VF minus VI divided by A, because that is true. Now, 3 is equal to D, VI, and VF, which is sweet because that's what we already had in there. T, this is another easy one. T is just equal to 2 times the displacement divided by the change in velocity. So VI2 minus VF2. Again, it's just a twisting around of those same functions. You guys can handle it. T is equal to 2D divided by VI minus VF. And I guess technically that's the negative delta V, because delta V is final minus initial. But it doesn't matter. Because ordinarily the final is going to be pretty high. Okay? 2 times D minus VI minus VF. There we go. Just making sure I don't get twisted. All right, now 4 is D, VF, and A as our known values, and to solve for T from those three, it's just equal to, uh-oh, am I twisted? Square root. This is one where we have to solve for VI again. Sorry, it's a long video. I'm getting a little confused. Okay, math.square root of VF squared, which is one of our knowns, minus 2 times A times D. Oh, I forgot a 2. I bet you guys caught that and I didn't. That would have given us an error later. It's not a bad time to check our other 2's. Okay. Those all look good. All right. So we solve for VI by saying it's the square root of VF squared minus 2AD. Check the formulas if you don't believe me. And then, now that we have VI, it's really easy to solve for T, because T is just equal to kind of that same exact thing we just did, 2 times D2. And I'm just reusing that one because we literally just used it. And then VI minus VF. Okay. And it's going to want to automatically reformat the file. And this is pretty easy now because, again, we are solving for VI first, which is actually conveniently what the already copied in work was doing here. And we just say it's the square root of VF squared minus 2 times A times D. And then we show what VI was calculated to be. And then we just say, therefore, T is equal to 2D divided by VI minus VF. And we are getting so close, you guys. Thank you for bearing with me. We are now just doing the D calculations. And I'm pretty sure that is it. So let's grab not the one we just did, because that had a quadratic equation and that was nasty. Let's just grab VF. I think that was pretty easy. And we're going to start from there for D. Okay, so now we're calculating the displacement, and we're going to say if D is in known, then set D equal to whatever was entered. Our work is going to be kind of sassy. And then if they don't give us enough information, we're going to tell them, hey, what do you expect us to do, more or less. And then the units for D are just going to be meters, and we can just say displacement. If you'd rather say distance, that's fine. I think displacement sounds a little more sciencey, and that's always the goal. And now let us do every combination of variables. So VI, A, and T is good for 1. VI, A, and F, final velocity is good for 2. We will say VI, VF, and T is good for 3. And then the only other combination would be VF, A, and T. What is happening, just in case things get confusing. And let's start with A, T, and initial velocity. So A, T, and initial velocity. I for sure did not have to change these, but I did. All right. So D is equal to initial velocity times the time that has elapsed plus, and then 1/2, so I will just type 0.5, it's easier, times A2 times T squared. So you don't need that. There we go. T star 2 and T2. Golly, the T's are hard for me. All right, there we go. So that's D. And for our work, we just explained that D is equal to VI, initial velocity, times time, plus 1/2 times A times T squared. There we go. And that's actually one of the harder ones to type. I mean, I think D is a pretty friendly variable, so it's kind of nice that we're ending on it. So A, VF, and VI are your knowns now, and to solve for D, all we have to do is say VF squared, just 1, 2, man, calm down, minus VI squared divided by 2 times acceleration is equal to displacement. That's pretty nice. It's just a riff on one of the basic formulas. And for work, we can just say VF squared minus VI squared divided by 2A. We should really include parentheses because we're not animals. There we go. But we're clipping right along. And don't forget your 2's, or it's going to throw errors at the end, and I'm going to be sad, and then we're going to just burn the place to the ground, I guess. Now, let's see. We are in Calc D. Okay, I was making sure I'm not getting twisted. We've done 1, and we have done 2, and we have not yet done 3. 3 is we know time, and we know final velocity, and we know initial velocity. So we have time, we have initial. Let's change that to final. Displacement is just D2 equal to, and then VI2 plus VF2 times T2 divided by 2. So this is a pretty easy one. It's basically the change in velocity combined times the time that has elapsed divided by 2. So D equals, and we basically tell them that. So VI plus VF over 2 times T. It really doesn't matter what order you do these things in. If you divide by 2 once you add these two together, or you multiply by T first and then divide by 2, because order of operations, those two things are basically equivalent. Check my math, look it up. I dare you. TA and VF are for Formula 4, and this is going to be the last freaking formula we have to type, but you guessed it, we have to solve for initial velocity first. VF2 minus A times T is going to give us VI, and now we have dealer's choice on how we want to solve for displacement. So let's use that easy function we just used a second ago, and VI2 plus VF2 times T2 divided by 2 is D2, 2, 2, 2, 2. That all looks good. And for our work, we just have to explain that VI is equal to VF minus A times T. If adding the work felt silly to you this whole process, just understand, like, showing how you got to somewhere is like really core to understanding what's actually going on behind the scenes. So maybe you don't need it, maybe you just want the answer, but most of the time seeing how the sausage is made can't hurt. So there we go. Now, if we did everything right, this can solve any kinematics problem as long as you have at least 3 known values. I don't think we're missing any functionality. I don't think there's anything we forgot to add. So this was a pretty cool project. Let's go ahead and run this, and let's just test it against some problems where we have known answers. So we're really just trying to solve... Oh no, did I close it? I had a bunch of good practice problems up. Here they are. Let me minimize this a little. Okay, so I have a bunch of problems from a website called physicsclassroom.com. I hope I don't get in trouble for using their site. This is educational, they're educational. You'll be seeing all the stupid ads on their website, just like you can on mine. I don't have ads, I don't think. Okay, let's go ahead and just look at this first one. So they're saying acceleration is 3.2 meters per second for an airplane. It accelerates at that speed for 32.8 seconds, and it starts from rest. So determine the distance traveled. That means we have initial velocity 0, time 32.8, acceleration of 3.2 meters per second squared, and we are looking for distance. So I'm going to hit D, and according to our program, it's 1721.34, and it shows you the function of how we got there. Let's go ahead and scroll down a little because I know this website has solutions. So you can even see, this is awesome. They say 1720. I'm sure it's just because our program is a little bit more accurate in terms of decimals, so that's just a rounding difference. But 1721.34, and we show the function of how we got there. That's the exact function that they needed to use. So I'm not going to read the actual word problems for all of these. I'm going to use these problems to check our calculator. So this second one, and I'm going to use my clear values button. It's way faster than typing them and deleting them. So for this second one, we're given dt and vi. So d is 110, t is 5.21, and initial velocity is 0. And we are looking for acceleration. And according to this, it's 8.1. Here's the function that got us there. And bam, you can see they even turn it around in the same way. So they just plug all these values in instead of like rewriting it. But understand, this function is how we got to this function. So ours is actually rewritten in a more logical way, but we get the same answer. So I'm not going to talk too much smack on them. All right. Now, this one, we are looking for D and we're looking for VF, but we were given T, so 2.6, initial velocity 0. And it looks like for this one, it's some kind of gravity problem because acceleration is negative 9.8. We're looking for D first. And according to this, it's negative 33.12. Bam. The negative means down. And then we want final velocity, and it's negative 25.48. This says 25.5, and negative means down. So this is sweet. There are a total of like 20 problems on here. If you want to check that your calculator is totally cash money, just find a website, type in kinematics sample problems online, and tons of websites will pop up giving you word problems where you essentially solve for these values. But you guys, this is an awesome project where programming meets physics. Cross disciplines of engineering are really where cool projects, I think, get developed the best. So hopefully you had fun if you were looking to expand your knowledge of physics, if you're looking to get better at Tkinter, if you're looking to get better at Python. If you had an hour and a half to kill and you said, hey, this looks interesting, thank you for being here. I hope you enjoyed the project. Let me know if you have any questions. Let me know what you want to see in a future video. Be sure to leave a like, subscribe to the channel for future content, and as always, thanks for watching and good luck with your code. Thanks, bye.